All right, for the last bit, just going to look at just some other graphs. There's some graphs that have appeared over the years, some of them a little bit different. This came from 2003. There was the random graph they gave us that particular year, and they asked us to draw different particular ones. So let's see. First one they said was the reciprocal graph. So reciprocal graphs, what did we know about that? We know x-intercepts became asymptotes. Well, we got no x-intercepts on this one. However, the asymptotes became x-intercepts, sort of. The other thing I'm going to do there, you'll notice, is I'll find on the scale. They've told me this turning point's 2. So I've worked out where 1 is, because that's one of the key points we're looking for when we're doing a reciprocal graph. So, okay, they become x-intercepts, sort of. They point discontinuities there. 1 stays at 1, so down there, -1 also stays at -1. And 2 becomes a half. Now, I know when it was below 1, it's above 1, and above 1, below 1, and so on. So from there, whoop, I can draw my diagram. So this one combines a couple of ideas. It's an addition of a graph, but also an absolute value. So we're going to get function x, and we're going to add absolute value of function x. So let's work out what absolute value of function x is first of all, so we know what we're adding. And absolute value of function x was whatever is below, reflected above. So we're adding the blue one and the black one together. Now, if I add the U shape, the beautiful, perfect U shape that we've got here together, obviously we're going to get twice the values. So 2 is going to go up to 4, and we'll still have a U shape going between the asymptotes. Question is, what happens out at the side? The mistake they made was to think, oh, well, clearly the reflection is going to cancel with the bit below, and just didn't draw anything because they thought, oh, it cancels. But it's not that it cancels. You add them together and you get... So actually, there's going to be 0 for all those points. Okay? So the common mistake was just to draw the U and forgot about those endpoints. They are actually 0. All right, let's do function x squared. Stationary points, we said the state of stationary points. Obviously, the y value is changing. 2 squared would be 4. We have no x-intercepts in this case. So, oh, that's a bit boring then, really, isn't it? 2 goes to 4. So that, again, you've got some sort of U shape. All those y values are squared. I suppose the only interesting thing about this one, with the bits down below, when you square it, they become positive. Something like that there. Oh, this one is fun. And these are the ones that are a little bit different. These other ones, where you get some other function involved, like an exponential or a log or a trig or something like that. So draw y equals e to the power of function x. Now, what I tend to do with these ones, I draw myself a little picture of the basic curve, replacing function x with x. So y equals e to the power of x. Just so I know what the key points are doing. So let's have a look at this. We can see that an exponential curve always has a y-intercept of 0. So whenever this curve is 0, it'll be 1. Now, this curve is never 0. However, it does have a horizontal asymptote at y equals 0. So therefore, my new graph will have a horizontal asymptote at e to the power of 0, which is e. So I know there's going to be a horizontal asymptote at e. What other key things? Let's have a look at the derivatives to see whether that picks up anything interesting. If I was to differentiate e to the function x, I get f dash x e to the function x. So I'm going to have stationary points. Again, they're going to remain because f dash x will still be 0. So I know there will be a stationary point at x equals 0. The y value will become e squared, because you're saying e to the y value is basically what you're saying, e to the power of function x. And whenever e to the function x is 0, well, e to the function x will never be 0, because our exponential is never 0, so there's no more stationary points created. Whoop. Again, in between the two asymptotes, we get that lovely U-type shape, because let's have a look at what's happening with these y values. The y value of the original graph is getting bigger and bigger and bigger and approaches infinity. So e to the power of the y value. Well, as the y values are getting bigger and bigger and bigger, the exponential curve is getting steeper and steeper. So it must be copying that exponential. So it might be a bit steeper than what I've drawn. It probably more like a exponential. Okay. Ooh, why has he drawn those in? Well, we'll see in a sec. There's our horizontal asymptote I was talking about. Okay, so I know out at infinity, this curve is approaching 0. The original curve. Therefore, my new curve is approaching e to the power of 0, which is 1. So the horizontal asymptote is 1. But what's happening here? Why did I put point discontinuities? Well, this asymptote saying this branch of the graph, let's have a look at the right-hand side. The y value is coming from minus infinity, if you like. Have a look at the exponential curve. Where is it at minus infinity? So this one's coming from 0. Well, you don't get asymptotes then. You've got a point discontinuity at that particular point. So it's going to start out from 1, and then it's going to bend towards the asymptote. There's two things it could do. It could either come out of the point discontinuity with a steep slope and remain concave down and bend towards the asymptote that way. Or it could come out of the point discontinuity with a shallow slope, but then it would have to have a point of inflection so it could then bend towards the asymptote. So which one of the two does it do? Well, if you have a look at the derivative that we found, so y dash was equal to f dash x times e to the function x. Well, as x approaches 1, that's what we want to do. We want to find that the slope as x approaches 1. Well, f dash x, or the derivative of the old graph, if you look at the picture of the original graph, then its slope is approaching infinity. So we know the derivative of the old graph is approaching infinity. But it's times e to the function x, which is the y value of the new graph. And we know that as x approaches 1, the new graph is approaching 0. So we have infinity times 0. Well, what's that? Well, now we look at the idea of dominance. We know the exponential will dominate. So therefore, the derivative of the new graph will approach 0. Well, that means it's a shallow curve, not a steep curve. So we know it was the second case. It's going to come out of the point discontinuity with a shallow slope, and then it will inflect and bend towards the asymptote. Let's have a look at 2002. There was an interesting mistake in this one people made too, which we'll come to. But there's random function. And you can see they've located the height of 1 for us and minus 1, so that'll be useful. First one they want us to draw is the reciprocal. So 1 over function x. Well, we know those x-intercepts will become asymptotes. We know at 1, it will stay at 1, and at minus 1, down there it'll stay at minus 1. The turning points will also remain. Oop. So above, well, all of this is above, so it'll go below and above. I think that's enough we really need. Oh, look. Shading in the areas, just to highlight above and below, below. That's where I'm going to draw my curve. Whee. There's our reciprocal. Y squared equals function x. What starts out as a very exciting graph, because you think, oh, look at all this I've got to work with. But of course, y squared equals function x starts from y equals the square root. And the first thing when we do the square root is we say goodbye. Bye. Ah, we just got that. Oh well, let's find the square root of that. By the way, that's the mistake people made. They forgot about naught. There's a single point at naught, because you can find the square root of naught. Aha. All right, over on the other section, square root of 1 is 1, square root of 2 is 2. That to me looks like it's cutting through straight. So square root of a linear function would be square root of a parabola on its side, that sort of shape. So because that's y equals the square root of function x, so we reflect it, and you can see now it's straight. It's just, yeah. No, but don't forget the point. Oh, look at this one. Absolute value of function, absolute value x. So whenever you're working with grouping symbols, you work from the inside out. So the first thing we draw is function absolute value x. So which one was that? Function absolute value x means we're only substituting in positive numbers. So the left-hand side, see ya. So we just got the right-hand side. And function absolute value x said whatever's on the right, reflect over. Ooh, there we go. Now, we're going to find the absolute value of that. Now, when it was absolute value, we said whatever's below, reflect it above. So below goes above. Interesting little graph, that one. Oh, the log of function x. The log of function x. So again, I'll just draw myself over here. A picture of the basic log curve so I can get a feel for what the key points are going to be doing. What do we notice? Well, log of 0 doesn't exist. So at all these x-intercepts, we're probably going to get a vertical asymptote like a log curve has. So we've got a couple of those. Log of 1 is equal to 0. So whenever this has a y value of 1, we know that's going to become an x-intercept. Can't find the log of a negative number. So underneath again will disappear. The curve, we've got numbers that are smaller than 1. When I find the log of numbers smaller than 1, we've got negatives. And then so it basically looks like we're going to have a log sort of shape in that section there. So let's draw that in. So the curve, something like that. So with those ones where it's the log or exponential, I like to draw the basic curve to the side so I can see what are the important features of this graph. All right, let's play with 8h. See how we go.